there is more than one form in which one might write the equation of a straight line. We're familiar with the slope-intercept form, y equals mx plus b. For a straight line, usually when I say find an equation of a straight line, write your final answer in slope-intercept form. That's an incredibly useful form if you're finding the slope or if you want to write in terms of a function. It doesn't include all straight lines, though. It leaves off the vertical ones. A line has to have a slope in order to have a slope-intercept form. This more general form catches equations of all straight lines. Ax plus by equals c. Basically, we look at the equation. If it has nothing but x terms, y terms, and constant terms, then it can be written in this form. And so this is the standard form of a linear equation in two variables. If we replace the equal sign with an inequality, four most popular inequalities are the less than, greater than, less than or equal to, greater than or equal to, then we have ourselves a linear inequality in two variables. And in this section, we want to be able to graph linear inequalities in two variables one at a time, and then maybe two or three at a time. So, linear inequality. And make it plural, because we can write four different ones. Let's see, I'm going to scoot this down here. Four different ones. Ax plus by is less than c. Ax plus by is greater than c. Ax plus by is less than or equal to c. Ax plus by is greater than or equal to c. Now each of these is going to involve the graph of the straight line, ax plus by equals c. That's going to be the boundary line for the solution region. There's a much greater portion of the plane, a set of points that are going to satisfy the inequality than there will that satisfy the equation itself. But the straight line is going to form the boundary of the solution region. Well, what is the solution region going to look like? If we take ax plus by equals c, we'll begin each one of these by graphing it, and probably need to go ahead and mention that it should be graphed either as a solid line or a broken line, depending on whether the inequality has the or equal to bar, as this one does and this one does, or doesn't, as this one doesn't and this one doesn't. Strict inequalities, or ones that have the or equal to bar. If it's one of these, it will have a solid boundary line. And if it's one of these, it will have a broken boundary line. Alright, so let's suppose it's a solid boundary line, and it looks something like this if we sketch the graph of ax plus by equals c. Well, any straight line that we draw in the plane divides the plane into two parts, all the points on one side of the line and all the points on the other side of the line. Each of those two parts is called a half plane. So you've got a big old half plane up here. Half plane, everything on that side of the line, and another half plane down here. And then you have the points on the line itself. If we look at these inequalities that are strict inequalities, the one with strictly less than, the one that's strictly greater than, every point on one side of that line, that is one of those half planes, will satisfy this one. And every point on the other side of the line, the other half plane, will satisfy that one. And the big deal in graphing these linear inequalities is figuring out which side of the line is the one that will satisfy that inequality, and that'll tell us which side of the line that we should shade as an indication of the solution region. Just have to pick one point and test it in the inequality itself to see if it works or if it doesn't. What we'll do when we get there is we'll test the point, and if it works, we'll shade that side of the line, because that'll mean every point on that side of the line works. If it doesn't work, what will we do? Shade the other side, because it'll mean the other side of the line is the one that is the solution region. So we'll graph the straight line, the boundary line, either as a solid line or a broken line, and then we'll pick a point, test it, and then shade the appropriate region. That's how these, when we graph them one at a time, that's how these linear inequalities will work. So let's look at this one. 5x minus 7y is greater than 0. It is a strict inequality. The first thing to notice is that we will graph 5x minus 7y equals 0. I think it's important to write it without the greater than. Just write it as an equal sign. That way we're actually thinking of it as a straight line. Graph this as a solid or broken? Broken. Because it does not have the or equal to bar. It doesn't have that there. Strict inequality. As a broken boundary line. Now there is more than one way to sketch the graph of a straight line. The way it's set up, it would almost look like x and y intercepts would help. But if we go looking for x and y intercepts for this one, we'll find that the graph goes through the origin. 5 times 0 is 0, 7 times 0 is 0, and 0 minus 0 is 0. So when the graph goes through the origin, we find the x-intercept, we find the y-intercept, and we have a total of just the 1 point, the origin. So it doesn't help us a whole lot, except to note that we do get the point that way. Another thing we can do is just kind of stare at the thing and hope an ordered pair occurs to us that might make it true. I don't know, any x's and y's jump out at you that might satisfy? What is it? I thought
35 would be the equal 35, so you do 35 minus 35, so 7 times 5, 5 times 5, and 5 times 7.
So what I'm hearing is x equals 7, y equals 5, because we've got the 35 thing working. Okay, that might work. If that doesn't work, and I believe what we'll find is the point 7, 5 actually is a point on the graph. A suggestion that was made in yesterday morning's class was that we take this and solve it for y. Basically put it in slope-intercept form, and we've already got the origin there, so all we need to do is use the rise over run idea to find one more point on the line, and then we'll have it. So that's what I did, and it worked pretty well. So if we write negative 7y equals negative 5x by subtracting 5x from both sides, and then divide both sides by negative 7, y equals, well, we can't reduce 5 over 7, but a negative divided by negative is a positive. So we can get from this that the slope is what? It is positive, and specifically, of course, 5/7. So when we're doing the rise over run thing, we know that we go 5 up, 5 over 7. That would be 5 up, and then trying to point at that 7 there, 7 to the right. So we can go 5 up, 7 to the right, and that takes us to that point. So here goes broken line, connecting those dots. And on this way as well. Incidentally, negative 7, negative 5 is also a point on the graph. And it looks like that. That's the boundary line. Broken because it's a strict inequality, does not have the or equal to bar. We're gonna shade everything on one side of the line, and we just need to decide which side of the line it is. Now what I'll usually do when the graph does not go through the origin is test the origin, just because it's easy. Substitute 0 for x, 0 for y. It's usually really easy to see whether or not that makes the inequality true. But this one goes through the origin, so we can't use that one, but there are a lot of other good choices. What's another point that we could use to test? 1, 0? 1, 0, keep it simple there. 1, 0 is right there. Is a test point, so test 1, 0. And it pretty clearly needs to be a point that's not on the line, and choose it so that it's clear which side of the line it's on. It's pretty clear that this point is kind of below and to the right of the line. So let's test it. 5 times 1 minus 7 times 0. Is this greater than 0? 5 minus 0 kind of looks like it is. We'll say yes. 5 is greater than 0. So the point 1, 0 is in the half plane. That is the solution region for this inequality. So we will shade everything else that lies in that half plane. So it'll look like this.
That test point that you came up with, why did you choose something that would be, can you just as easily choose 2, 1?
2, 1. Now 2, 1 would work, but 2, 1 is so close to the line that I would worry that it might be difficult to tell which side of the line it's on. 2, 1 is right there, and it looks like that would work because it pretty clearly, I guess, is below and to the right.
Okay, then I said it backwards. 1, 2.
1, 2.
Yeah, I'm trying to.
Yeah, 1, 2 is up there.
Okay. Yes.
If we had selected 1, 2, and we had tested it, would it have made the inequality true or false? It would have worked as a valid test point. Before choosing the test point, is there any way to predict whether it's going to make it true or false?
Right.
Am I substituting this correctly, by the way? What's that?
I think so.
Negative 9 is greater than 0, and so it's a no? Okay.
I understand how it works now, but
Right.
just choosing it, is there a way that you can just look at it and say, I should pick a point below that line or above that line?
I guess the point is that it doesn't matter. It doesn't matter. Just choose a convenient point at random. If it didn't go through the origin, I would choose the origin just as a rule because it's easy. And if it works, you shade that side of the line. If it doesn't work, then you shade the opposite side of the line. Yeah. So don't worry about whether or not it's going to work, because either way, it'll give you the information that you need. Okay. Example 2, a little bit different, I think, insofar as coming up with the graph of the boundary line. 2x plus 3y is less than or equal to 6. So we want to graph the equation 2x plus 3y equals 6 as a broken or solid? Solid. Solid boundary line. Because if 2x plus 3y equals 6, we find an ordered pair, an x and y put together, such that 2 times x plus 3 times y equals 6, then 2x plus 3y is less than or equal to 6. If it satisfies the equation, it's going to satisfy the inequality because it has the or equal to bar. So solid line to indicate that points on the line itself are solutions to the inequality. Now for this one, I'm going to suggest that we use the x and y intercepts. Of course, if we wanted to solve the equation for y, it would not take long. We could find a slope in the y-intercept. We could plot the y-intercept. We could use the rise over run idea to find one more point very quickly and sketch the graph. It's really a matter of one's personal preference, but I think with just a little bit of practice at a glance, you can see the x and y intercepts here, and so it's a reasonably nice way. Officially, we're letting y be 0. All the points on the x-axis have different x coordinates, but they all have a y coordinate of 0. So if we let y be 0, 2x plus 3 times 0 equals 6. 2x plus 0 equals 6. If 2x equals 6, x would have to be 3. So the point where the graph, the point where the graph crosses the x-axis is the point 3, 0. And if we let x be 0, all the points on the y-axis have different y coordinates, but they all have an x coordinate of 0. 2 times 0 plus 3 times y equals 6. 0 plus 3y equals 6. And 3y equals 6, y would have to be 2. So put the x equals 0 and the y equals 2 together, and so the graph goes through the point 0, 2. Do we connect the dots with a solid line? And we choose the test point. I like the origin in this case because this graph does not go through the origin. The origin is clearly below and kind of to the left of the line. So test 0, 0. Now, as I'm doing this, I'm going to write the inequality and I'm going to include the or equal to bar. However, when we choose a test point, it really must be a point that's not on the line. So if it comes out equaling 6, something horribly wrong has happened. And we won't, if we say yes because it's actually equal to 6, this would not give us the information that we need. We need it to be less than 6. So we're wondering, is it truly less than 6? And 0 plus 0 does appear to be less than 6. So this is a yes. And so again, the test point fell in the half plane, which is the solution region. So we will shade everything in the region from which the test point was selected. Had we chosen 7, 5 or something up there, it evidently would have made it false. 2 times 7 is 14, 3 times 5 is 15. So 14 plus 15 is not less than 6. So that would say don't shade above and to the right. Instead, shade below and to the left of the line, which we did. Are these hard problems or easy problems?
Easy.
Easy problems. Love to hear that. Oh, an even easier one. Special case. Special case. Example 3. Graph x is less than -2. Now, when I write the standard form of the equation, straight line, ax plus by equals c, this works so long as a and b are not both equal to 0. Now, usually, a will not be 0, and b will not be 0 either, and it'll give us a slanted line. But if either a or b happens to equal 0, then it does not give a slanted line. Either it gives a horizontal line, in the case when a is equal to 0, and we just have a y but no x, or it gives a vertical line in the case that b is equal to 0, and we have an x and no y. So we want to graph x equals -2 as a solid or broken? Broken boundary line What does this line look like? It's a straight up and down vertical kind of line. If we just plot a bunch of points that have -2 as their x coordinate, there's one, and 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 there's one. We can see what this line looks like. So broken line, x equals -2. We can choose a test point if you'd like to, or just think about it. Which side of the line is going to contain points with x coordinates less than -2? To the left. -3, -4, -5, -6. Those are less than -2, and those are going to be found to the left. So I really don't think in the case of these vertical lines, or in the case of a horizontal line, that we really need a test point. Greater than means to the right, less than means to the left, or in the case of a horizontal line, greater than would mean above, less than means below. So the picture looks like this. No test point needed. Now, the key problems that we really look at in this section, the title of this section, is systems of linear inequalities. So what we'll do is consider 2 or more of these inequalities at the same time. We will shade them individually, and then the solution to the system is going to be what the shaded regions all have in common. We'll see where they overlap, their intersection basically. Example 4. moderately nice one here, I guess, because the straight lines are not too tough to graph. Now, I'm going to graph both of these on the same set of axes, and then I'll shade them one at a time, and then they'll both be shaded, and we'll look and see where's the cross-hatched region, what got shaded both times, and then I'll erase. So the suggestion would be on the test question, maybe use some scratch paper if you like to shade them both and just see where the shaded region is, the overlap, and then on the actual, I'll give you either a grid or an X and Y axis. Then copy it over and only shade the region where they intersect. Or if you have a good eraser, you could actually use that space and then carefully erase everything. But you don't want to have anything in any region that's not part of the final answer that's shaded if it's not supposed to be shaded. Only the solution region should be shaded at all. So let's look at x plus y. X plus y equals 5. Not too tough to graph. This is going to be a solid boundary line. At a glance, we can see the x and y intercepts, yes? 5, 0, 0, 5, because 5 plus 0 equals 5, and 0 plus 5 also equals 5. Connect the dots. Does the origin make this true? 0 plus 0, is it less than or equal to 5? I'm thinking yes. So we'll shade everything in the half plane containing our test point. Okay, maybe the other one will be a little bit more of a challenge. Another solid boundary line. X minus y is equal to 6. If y equals 0, what's x? 6. So we'll go 6, 0 for the x-intercept. And if x equals 0, what's y? Negative 6. So down here, 0, negative 6. So we'll connect these dots. With a solid line. And check the origin again. How about 0 minus 0? Is that less than or equal to 6? I need to choose some examples maybe where the origin does not work. Oops. But while it does work, I need to indicate that it does. Yes, this is a true statement. 0 is less than or equal to 6. So again, we shade everything in the region containing our test point. That's everything above and to the left of this line. And the solution region, the final answer, is a set of points that satisfy both of these inequalities, where x plus y is less than or equal to 5 and where x minus y is less than or equal to 6. Has got to satisfy both, and the points that satisfy both are in that region right there. So the cross-hatched region, or whatever got shaded both times. Oops. There's 5, 4 right there. Let's look at question 7. And maybe one more. Question 7 gives us the boundary lines. It gives us 3 inequalities, and it gives us boundary lines that go with those. Seven regions to choose from. And we want to see which region it is. When I looked at this problem yesterday morning, it ended up being region A. I'm a little concerned that it may be that again, but maybe not. Let's look and see if that's the way it works out in this case. I did similar exercise after I completed that example, and it did reverse the direction of some of those inequality symbols. So based on the choice, the random selection of the direction of the inequality symbols, it could be another one of these regions. So let's look at them. Let's look at, okay, x plus y equals 2 is the red line. So let's see which side of the red line to shade. Does the origin, see the origin is not on any one of these lines, so it can function as our test point for all 3 of these. Does the origin satisfy 0 plus 0? Well, the origin is going to satisfy all 3 of these, isn't it? So it's going to be region A. That's not very interesting. I'm going to close this. I'm going to say A, check, great. Similar exercise. The origin satisfies all 3 of those too, doesn't it?
I was going to say I can almost guarantee it's
Save it. Actually, no. I can't cancel out of that, can I? Best score. I can get back to it. Come on, similar exercise. I guess I have to answer it. I have to say A. I have to say similar exercise. Okay. Aha! It reversed some of the inequalities. Now, greater than or equal to -1 doesn't help us a whole lot. But the greater than 3, I think, kind of helps us a little. Because the origin's still in the middle. But I don't think this one is going to be A. Let's try this instead. That's satisfactorily covered up. I think so. Okay. Now let's test the origin. How about, so the red line is the top one, yes. So 0 minus 2 times 0, is that greater than or equal to 3? No. So we would shade the side of the red line that does not contain the origin, since it was a no. Now let's see what's next. The black line. Test the origin again. How about 4 times 0 plus 3 times 0 is greater than or equal to -1? That is a yes. So it looks like we will need to shade above and to the right the black line, like so. And for the blue line, test the origin. It's going to be 3 times 0 plus 0 is less than or equal to 8. It would appear that it is. So that's a yes. So we shade the side of the line containing the origin, and it looks like this. Kind of messy, I guess. C got shaded all 3 times. In C, I see blue marks and red marks and black marks. D just has red and black. B just has red and blue. A just has blue and black. E just has black. G just has blue, F has none of the above, so it's going to be C. Oh no. Check it. There we go. Okay. And there are others, like problem 6. What if the lines are parallel?
They don't understand.
The lines themselves don't intersect, but there could still be some solutions. Basically, when you look at the test points, you could very well come up with, I mean, this was interesting to me. I don't know if the answer is D or not, but if these are broken lines and nothing is shaded, that means there are no solutions at all, because the points on the lines themselves are not included, and there's no shaded region. The lines are just kind of there, probably because we'd sketched them in order to do the test, but then we realize there are no solutions at all. So it's curious to me, the picture actually could have been left completely blank, and that would mean exactly the same thing. But as you're testing, suppose you do a test point, and the result of the test is you shade, let's go blue. You shade this side of the blue line, and you do a test point, and the direction the inequality symbol is pointing, you shade that side of the red line. In that case, what's the solution set?
All Romans.
That would be, well, in this case, you ask what they have in common. And in this case, they have nothing in common. So it would be answer D, nothing at all, the empty set, basically. There are a couple other cases, but let's consider kind of the antithesis of this one. Suppose we're checking, and we test blue, and it's this side of the line. And we test red, and it's this side of the line. What would be the solution region in that case? It would be, what got shaded both times? Let's see, purple is not an option. But it would be what they have in common there. That's where they overlap in that case. But it might not end up being that. It could very well be if we test red and it's everything above and to the right of the line, and we test blue and it's also everything above and to the right of the line. What would the solution region be in that case?
The upside of doing that.
Yes, so whatever got shaded with blue, because whatever got shaded with blue got shaded also with red, but the little sliver that got shaded with red did not get shaded with blue. So it would just be, it would be this right here. And that would be the solution region. So you look to see what they have in common. There are several cases, even if the lines in question, the boundary lines, are parallel. All right. There's 5.4. I think we should probably take time and talk about everything else to expect on the test. So the review has been there. The solutions, I guess, are somewhat new as of yesterday morning. So let's look for those. Actually, no. The review is new too. The review and solutions both showed up right before 8 o'clock yesterday morning. So these topics, I want to expand on a couple of these. I think this would be good as practice test. These problems in this review, that it's approximately the same length as the actual test would be. But there are a couple of problems that you want to think about that aren't specifically mentioned on this practice test. Consider the objectives, given 2 points. Find the distance between the 2 points. Back in section 2.1, basically, we looked at the distance formula and the midpoint formula. So if I want to begin building a formula list, just a few basic ones for this test. D equals the square root of x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. The distance formula. In that same section, we looked at the midpoint formula, where we average the x-coordinates to find the x-coordinate of the midpoint, and average the y-coordinates to find the y-coordinate of the midpoint. And I don't think there was a whole lot of additional excitement in that particular section. 2.1, we looked at those formulas, kind of derived both of them, but then we moved on. Section 2.2 had to do with testing. Close these out. It'll let me. It may not let me. Why is it not letting me? Leave it. Testing equations for symmetry. If we're looking at an equation with x's and y's in it, we may have no idea what the graph looks like, but there's a nice, fairly simple test to determine whether or not the graph of that equation has x-axis symmetry, y-axis symmetry, origin symmetry, all of the above, or none of the above, those 5 possibilities. And as you'll recall, if we're suspecting that it might have y-axis symmetry, we can substitute negative x for x, simplify, and let's see, in the solutions down here,
If we get the same equations.
then it does have the symmetry. If we get back what we started with, it will have that symmetry. So this A part, kind of rough looking equation there, x cubed plus y squared minus xy squared, I tested for x-axis symmetry by substituting negative y for y, and that came back a yes, because it gave back the original equation. Tested for y-axis symmetry by substituting negative x for x, simplified, and that was a no. It did not result in the original equation or something equivalent to it. And for origin symmetry, you do both at the same time. Substitute negative x for x, negative y for y, simplify, and in this case, it did not give back the original. So we would say that particular equation has a graph with x-axis symmetry, but neither of the other two. So carry out that process. Make sure you can show your work. I mean, it's nice if you can punch into the calculator and look and see, yeah, that is y-axis symmetry or origin symmetry. But you want to be able to show your work by substituting the negative x for x, negative y for y, simplifying, and show it does have the kind of symmetry that you think it might have. Section 2.2. Also in section 2.2, we did circles. Now, when I've listed these topics, it seems like circles got listed a little bit later than that. No, it was right there. Equation of a circle. Now, there are basically 3 ways this problem could show up. And I think only one of them is represented on the practice test, but be familiar with all these 3. The standard form of the equation of a circle is x minus h quantity squared plus y minus k quantity squared equals r squared. So, I don't know, perhaps the simplest way is if the information is given, center 5, negative 8, radius, length 4, and you write an equation of a circle that has its center at 5, negative 8, and the length of any one of its radii is equal to 4. Maybe good to go ahead and put something squared over there. How does it go? What's the equation?
X equals y squared plus x.
Oops, it is y. Thank you. Ah, there we go. Y plus 8. I was worried about the sign there and missed the variable. Y plus 8 quantity squared equals 4 squared. And not much to simplify there. Just square the 4. It's 16. On the other hand, suppose the equation looks like this. Can you look at it? I guess I should make up another one, huh? Kind of spoiled that one. X plus 3 quantity squared plus y minus 6 quantity squared equals 121. What is the center of this circle? And the radius length? Excellent. And then, oh, what if it goes like this? X squared plus y squared minus 6x plus 10y minus 14 equals 0.
You have to join x squared minus 6x plus,
Yep.
and then you have to figure out what the square would be.
Like that, like possibly fit numbers in those boxes. So to complete the square, x squared minus 6x plus what? And then y squared plus 10y plus what? Equals 14 plus 9 plus 25. So x squared minus 6x plus 9 is the square of what binomial? And y squared plus 10y plus 25 is the square of what binomial? And 14 plus 9 plus 25 equals 48. Oh, missed it by 1. All right, 48. We'll go with that. So the center, 3, -5. And the radius length is the square root of 48. And let's see. Square root of 4. Square root of 4. Square root of 16. Let's go square root of 16. Times the square root of 3. So 4 times the square root of 3. That'd be one way to write it. Or 6 point what? 6.9? 6.9? Okay. So circles. Those are hard problems or easy problems? Easy problems. We'll find some hard problems for this test. Don't want you to get bored. Worst thing, get bored taking an algebra test. Hate it when that happens. More formulas. Let's see. There is the slope formula. M equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Give it 2 points. If the x coordinates are different, you can find the slope using this formula. Y minus y sub 1 equals m times x minus x sub 1 is called what? Point slope. And it's good for finding what? Finding, what did you say? Well, you find the equation of a line, and ultimately the y-intercept will show up there if you put it in slope-intercept form. But in general, given a point and a slope, you can use the point-slope form to find an equation of a line, so long as it's not a vertical line. Y equals mx plus b will be the form that I'll ask you to put your final answer in. So you simplify the right-hand side and solve for y, and they'll put it in slope-intercept form. Various different ways the information can be requested. Let's see what it looks like here. Find an equation of a line that goes through 2 points. So that's a great question because it uses all 3 of those forms and formulas. Find the slope. Then pick either one of the 2 points, put it together with the slope, use the point-slope form, and find the equation, and then solve it for y. Put your final answer in slope-intercept form. Also, 6a and or b, you're given a point and an equation that's either parallel to the line that you want to find or perpendicular to the line that you want to find. So that's enough information to figure out the slope of the line that you want to find. Yes?
Do we have to use point slope form for the equation of parallel line or the equation for perpendicular one?
It is not absolutely necessary. There are nicer ways actually of doing it.
Y equals mx plus b.
Right. And just find b. It's not, that method is not recommended because it involves solving an equation to find an equation rather than just substituting. But if you do it correctly, then you get full credit. So it's more difficult to assign partial credit if it's not an approved method and it goes awry. But I'm confident that it will go well, and no bad will come of it. So as long as it works out all the way to the end, it should be fine. What is the slope of any line that is perpendicular to this one?
-1/2.
-1/2. So you look at this equation and you think m equals 2. And then you think opposite reciprocal. Take the reciprocal of 2, you get 1/2. Change the sign, you get -1/2. So -1/2 would be the slope that you would use for the perpendicular line. Can you do problem 7? Is it yet the easiest problem on the test? We should get to the point, punch enough buttons until it's the easiest problem on the test. If we're not there yet, we should do one more.
Yeah.
Yes. We could do this one. We could do number 9 and the homework again, or we could do the cricket chirping problem. Did we ever completely do the cricket chirping problem?
Yeah, we did.
We did.
Yeah.
All right. We didn't do the cricket chirping problem?
Yeah, we did.
We did? All right. So which one? Want to look at this one?
Yeah.
We should look at this one just to make sure I got the answer right. So let's see. Has everyone turned off your stat plot? If not, it's a good idea. I probably do want to view the key press history. Okay, stat button, number 1 on the list, edit. And then I've got numbers there, probably not the numbers I want. So press the up arrow, go to the L1, and do not press delete. Press clear, and then down. And then press the right arrow and then up. And do not press delete. Press clear, and then down. And then you can type the numbers there, 25, 38, the X values. Is there anything after the 86, I wonder? Nope, that's it. Once you get to the bottom of the L1 list, press the right arrow, go to the top of the L2 list, and then enter the Y coordinates. Once you get to the bottom of the L2 list, make sure you have the same number of numbers in each list so you do not get the dreaded dimension mismatch error. And make sure your numbers match the numbers that are given. And they appear to. Second mode button, second quit. I don't think it's absolutely necessary, but a lot of times it's a good idea to get back to the main screen. Once you get back to the main screen, you can have the calculator find the linear regression equation by pressing the stat button, followed by the right arrow to go to the calculate menu, followed by number 4. When you do linear regression of the form AX plus B. On the older operating systems, it will display lin reg AX plus B at the top, and you just press enter. Newer operating systems, it says all of this, getting you to confirm that sure enough, we're going to look at the L1 list and the L2 list, and then calculate. Enter. Okay, so make sure you press enter and look for these numbers. Do you see these numbers? A equals 1.79. That's the slope of the line of best fit. And B equals negative 2.84. That is the y-intercept. So when you write final answer, let's see what it looks like. Problem 7, is that what I got? Y equals 1.79x minus 2.84. 1.79x minus 2.84. So that's it. Ridiculously strong linear fit. Evidently these points were chosen by a math teacher and not someone in touch with reality. In real life you'd never have points that close to being on a straight line. But good enough. It's a good enough example here. Now, if x equals 115, can you find the y value that goes with that? Yeah, you can predict it just by substituting 115 for x, multiplying by 1.79, subtracting 2.84, and sure enough, 203.01. If I punch the buttons correctly on the calculator, hopefully that's the right value that goes with that. From that point, let's see. back up here. You solve a system of linear equations in two variables. Elimination method or substitution method. I'm not going to require a particular method. If one seems to work better than the other, if substitution method will work without producing unsightly fractions and you like that method, go with it. Otherwise, the elimination method should work. And you get a unique solution for problem number 8. For problem number 9, also a unique solution, but setting it up is part of the problem. So I'll probably ask you to set up a suitable system of linear equations in two variables and then solve the system to find the answer. So it's great. In fact, it's excellent if you can kind of guess and check your way to an answer that works. But I'll also want to see a system of equations to go with something like problem 9. And then problem 10 is like what we did today. So that would feel a little bit redundant if we looked at problem 10 right now. How do you feel about the setup of problem 9? Have you done enough of those where you have a high level of confidence looking at problem 9, looking forward to that problem on the test?
Yeah, I think I might be able to do it, but
Confidence, maybe not a high level of confidence, but confidence for sure.
All over the homework.
Yes, you have plenty of those on the homework after 5.1. The solution there, I used C and V for the number of pounds of chocolate, number of pounds of vanilla. We want a total of 100 pounds of candy. So C plus V equals 100. Maybe 40 pounds of one, 60 pounds of another. The value of the chocolate candy sells for $3 a pound. So $3 a pound times C is the value of the C pounds of chocolate candy. $5 a pound times V is the value of the V pounds of vanilla candy. And the total value of all 100 pounds of candy, right, is more than just $3.80. Definitely multiply by 100. 100 pounds of candy sell for $3.80 a pound. It ought to be worth about $380. So that's the setup. And to simplify the bottom equation a little bit, you can lose the dollar sign since every term on both sides has a dollar sign in it. You can divide both sides by a dollar, lose the dollar signs, and have something like 3C plus 5V equals 380. And the elimination method probably would work as well as the substitution method, whichever one feels better to you. I would go with it and find the values of C and V and check them, make sure they work. Should I finish it?
There's another kind that was in the homework though where you set up a table. Is it the same kind of thing? Is it a different way or is it a different?
It could be
Like
the calories. Yeah, the calories, carbs type problem. The setup is a little bit different. I think the setup on those is a little bit more straightforward. Basically, they give you a number, and they just fit naturally into a problem like this. This one I think is a slightly less intuitive until you do a half a dozen of them, then it's to the point of redundant. But I think the calories and carbs and what was it? Spaghetti and meatballs and lettuce. Iceberg lettuce. Yeah. The setup on that is more straightforward, I think. And we can look at one like that, but I think I'm gonna lean more toward the mixture problems for this particular text. Any other thoughts? Particular problems you'd like to see? Homework problems that you just, goodness, every time it gives me that homework problem, I never can do it. Which one is it that makes you feel that way?
Maybe you're just too good a teacher.
Well, with that,